Finding polynomial functions given zeros. There's a few concepts that we're going to cover before we jump into some examples, the first of which is linear factorization. Linear factorization for polynomials tells us if we take some polynomial, for example, p of x, we should be able to express it as a product of linear factors. So let's say we have something like x plus z sub 1 times x plus z sub 2 times x plus z sub 3 up to x plus z sub n, where z sub j, where j is of subscript 1, 2, 3, all the way up to n, represents some complex zero. So once we've identified solutions to our polynomial or zeros to them, we can after that generate a linear factor. So for example, if we have x equals 4, for example, as a solution, we can say, well, we know a factor would be x minus 4, and we can take that factor and multiply it by all the other solutions in our equation to get a factor or linear factored form for our polynomial. So that's one of the things we're going to be using to generate a standard form polynomial of oftentimes least degree given some number of zeros. And the second concept is conjugate root theorem. The conjugate root theorem tells us that imaginary and irrational solutions come in conjugate pairs. So there's two pieces that we should break down here. The first of which, what is a conjugate? So our conjugate is when we have binomial terms of equal, or that are generated by two equal terms. So if we're comparing two binomials, so we have something like A, B, A, and B. So these are the two terms that constitute the binomials. And one has an arithmetic operator, say addition, its conjugate, the other one should have the opposing arithmetic operator, in this case, subtraction. So these two things would be considered conjugates to one another. So once again, when we have a binomials, or two binomials with equal terms, in this case, A and B, and in between them are opposing arithmetic operators, that's how you identify a conjugate. Now, in this case, we're going to be looking specifically at imaginary and irrational values. So if we look at the form for an imaginary number, we can express it as, say, a plus bi. So here we see that we have a binomial expression. And if we want its conjugate, it should have the same terms. So it'll be a and bi as well, but the opposing arithmetic operator. So if it's plus, we're going to have a minus. And these two things, again, would be conjugates to one another. And for the irrational, we can express an irrational number as a plus b root c. So its conjugate pair, same terms, binomial, opposing arithmetic operator, a minus b root c. So how is that going to be used? Let's say, for example, we determine a solution is 2 plus I, then we automatically know that 2 minus I is also a solution. If we determine that the square root of 5 is a solution, which can be thought of as 0 plus root 5, by the way, we know that negative square root of 5 is also a solution. We have to be careful not to consider rational values as having conjugate pairs for solutions. So if we find x equal 1, then it's not necessarily true. Students make the mistake of thinking negative 1 is also a solution. So it's only imaginary and irrational zeros. And then one final note for a concept that we'll want to be aware of is the fundamental theorem of algebra, which tells us the degree of the polynomial will dictate how many complex zeros we expect to have. So now that we've covered those three main things, we can jump into some examples. So here's our first example. What is a quadratic equation in standard form with rational coefficients that has a root of 5 plus 4i? So if it's quadratic, we know that there are two zeros present from the fundamental theorem of algebra. We're given 1 0, and we can identify that that's an imaginary solution So a conjugate pair should also be present, 5 minus 4i, sorry. And there are two solutions. So once we have those two, this now just becomes an exercise of polynomial multiplication. So we have x equals 5 plus 4i, and x equals 5 minus 4i. And from these two zeros, we can generate linear factors. So by moving things back to the left and setting these equal to 0, x minus 5 minus 4i is equal to 0, and x minus 5 plus 4i is equal to 0. We've now just identified linear factors where we have a complex 0 in there, and we're going to have this polynomial, doesn't say how to name it, so we'll just call it p of x, can be expressed as x minus 5 minus 4i times x minus 5 plus 4i. So here we're using that linear factorization theorem. We use the conjugate root theorem to generate the two zeros, or find the missing one that wasn't given to us. Now we have the polynomial expressed as a product of two linear terms. Now we actually do this multiplication out to reveal the quadratic that would be responsible for those two zeros. So we have a triple distribution here. If I distribute the x first, we're going to get x squared minus 5x plus 4ix. Then we distribute the negative 5x plus 25 minus 20i. And then finally the negative 4i minus 4ix plus 20i minus 16i squared. Now we're told we were supposed to identify a quadratic with rational coefficients, and we'll see some imaginary terms in our polynomial here, but what we'll notice is they cancel out. And this should have been 4ix. So this 4ix and this negative 4ix cancel. This 20i, or negative 20i and positive 20i cancel. We still have an I term at the end here, but we know I squared is negative 1, so this becomes positive 16. And now we can combine like terms, and we'll get x squared minus 10x after combining these. And then if I combine the constants, we'll get plus 41. And now we have a quadratic polynomial with rational coefficients with those two zeros, 5 plus and minus 4i. Into our next example, we now need to come up with a polynomial function of degree 4, so we expect 4 zeros. Rational coefficients again, we're going to call it p of x as the roots 3 minus root 2 and 5i. So 3 minus root 2 is a solution. That's an irrational solution, so it's conjugate pair, 3 plus root 2. If 5i is a solution, it's conjugate pair, minus 5i is also a solution. Again, 0 plus 5i is how you could observe that to identify that binomial. And then using what we defined as conjugates, binomial of same terms, opposing arithmetic operator, we don't need the zeros, and that's where that minus 5i is coming from. So we expect 4 solutions because we're told it's degree 4. Here are our 4. Now we're going to use that linear factorization theorem by generating factors from these zeros. So we're going to have x minus 3 plus root 2, x minus 3 minus root 2, x minus 5i, x plus 5i. If we multiply all of these together, that's a linear factorization that represents our sought-after polynomial. Now, when it comes to multiplying this out, we have 4 things to multiply. I'll tell you that if we multiply these two with the irrational solutions and these two with the imaginary solutions, the result of each will only have rational coefficients, and then we can multiply those two quadratics together to get our 4th degree polynomial. That way we don't have to mix and match irrational numbers and imaginary numbers, and it becomes a big mess. So multiply the 2 with the irrational, multiply the 2 with the imaginary separately. It'll remove all of those irrational and imaginary numbers, and we'll get just rational coefficients. So if we take care of the first two, distributing x and distributing the negative 3, and distributing the square root of 2, And then it's square root of 2 times square root of 2, which is just 2. So that's after the first one. So maybe I should just say, we'll break this down. So this will take care of this multiplication up here. So distribute the x. You'll see that our imaginary numbers cancel here, I squared negative 1, so plus 25. So in the end, we just get x squared plus 25 by multiplying those last two. We have this x root 2 and this x root 2 canceling, 3 root 2, 3 root 2 canceling, exactly what we want. We can combine like terms, and we're going to get a quadratic x squared minus 6x plus 7, and we're going to have to multiply that by x squared plus 25. So as we expected, all rational coefficients to work with now. We're going to distribute the x squared. So we're going to get x to the fourth plus 25 x squared, then distribute the negative 6x. So minus 6x cubed, and then minus 150x. And then we're going to distribute the 7x squared, and then 175. We're going to combine like terms and put it in standard form. So the cubic term will come next. We'll combine the quadratic terms into 32x squared minus 150x plus 175. And here is our degree 4 polynomial that has those 4 zeros. Now for our final example, write a polynomial function of least degree with real coefficients in standard form that has the given zeros. So we're going to make up a couple here. Let's say that we have the given zeros x equals 2 and x equals negative 3, and say x equals 1. So if these are the only zeros given to you, don't fall into the trap of thinking that there's always going to be missing zeros. I have to come up with conjugate pairs in the problem. All three of these are rational solutions. So there are no conjugate pairs to any of these. So this polynomial only has these three solutions. There are no others to be found. So the factors are x minus 2 times x plus 3 times x minus 1. Multiplying these together should get you your polynomial. So this is a quick example I wanted to bring up because, again, we don't want to make the mistake of thinking rational solutions have a conjugate pair. That's only for irrational and imaginary solutions. So you just multiplying these three together will reveal the cubic that's responsible for these 3 zeros. Now, one thing about multiplying these is don't try to do it all at once. Whenever we do polynomial multiplication, we're only ever working with 2 things at a time. So we can multiply these 2 together, and then as a result of that, whatever that is, we're going to multiply by x minus 1. So that first double distribution, x squared plus 3x minus 2x minus 6, combining like terms, now we take that and multiply by x minus 1. So only 2 things at a time. Distribute the x squared, x cubed minus x squared plus x squared minus x, minus 6x plus 6. Just double checking that. That looks good. So x cubed, these actually cancel in this case, minus 7x plus 6. These are the solutions, or this is the polynomial that has those 3 zeros. And let's finish off the video with one final case. We haven't mixed and matched rationals with irrationals or imaginaries, but let's say we have x equals negative 2 as a solution, x equals 1 plus 3i is a solution, and x equals square root of 6 is a solution. So in this case, 3 solutions given. The last 2 are in the category of imaginary and irrational respectively. So we know there's a conjugate pair. So x equals 1 minus 3i. Again, binomial, same exact terms, opposite arithmetic operator in between. This root 6 can be thought of as 0 plus the square root of 6 if you're having trouble identifying the binomial structure and how you should change it to its conjugate. So we're just going to have minus root 6 because we don't need the 0. And here are our 5 solutions. Notice there's no pairing with the rational because that's not a part of our conjugate root theorem. And these are the 5 we have to multiply together after generating the factors from these zeros. So we'd have x plus 2, x minus 1 minus 3i, x minus 1 plus 3i, x plus, we'll go in order, minus root 6 and x plus root 6. We'll call this polynomial p once again, and us multiplying all this out is going to reveal the desired polynomial. Now, when we do the multiplication, we should only be working with 2 at a time, but how are we going to pair these things up? Pair up your imaginaries to remove all imaginary coefficients. Pair up your irrationals to remove all irrational coefficients. Then you have 3 to work with, and then still 2 at a time, but you should be down to only rational coefficients. So if we multiply this middle pair, we're going to get, by distributing the x squared minus x plus 3ix, and then negative 1 minus x plus 1 minus 3i minus 3ix plus 3i minus 9i squared. The i's should cancel. I squared is negative 1, so this is plus 9. Combining like terms, that's where we're going to get from multiplying the middle 2. Now if we multiply these last 2, distributing the x, now at this point, how you pair them up doesn't matter, but you'll see that we were able to remove all imaginary and irrational solutions. Working from here, again, only 2 at a time. You can multiply these 2 first if you'd like, and then multiply the result by x squared minus 6, or you can multiply these first 2 if you'd like, and then multiply that result by x plus 2. But I'll stop the video there. I think you get the concept by now. So we used a couple theorems. This is really just an exercise in polynomial multiplication, using some knowledge of imaginary numbers like I squared, knowing how to multiply square roots, but that is how you identify polynomials when given zeros.